Okay, so I'm continuing on with the 2017 Engineering Studies HSC, and we're going back to here. We're continuing on with question 22D, so I was kind of caught off guard and that interrupted. So we're talking about the difference between the two areas. So the area that we get overall is 188, and we just use our formula, 3,000, so we're using newtons, never kilonewtons, for when you're doing force over area. Now, you'll notice that they're using grease units. Yeah? So haven't converted that to meters squared. They've used millimeters squared, right? And if you use millimeters squared, we have the song, we go together like megapascals and millimeters squared. Okay, so moving on to the next question. I like this question. I put this in my Year 11 prelim. Okay, I don't want to spend too long going through it because actually no, I think I have an answer drawn up. Hold on. Okay, so here's one I prepared earlier. So if we go 0 up the top, so first of all, what kind of gates do we have here? We have, this one's a NOR gate, right? So it's an OR gate with a NOT dot, and this one is an NAND gate. It's an AND gate with a NOT dot, and here we have an AND gate at the end. Okay, so for the first example, we have 0, 0 going in. Well, the OR gate's going to say, look, sorry, neither of you are on the list, you're not getting in. But the NOT dot goes and messes things up and flips it to a 1. AND gate, same thing. Look, you both need to be on the list. I'm sorry, that's not the case. You're not getting in. The NOT dot flips it and makes it a 1. So the first one's going to be 1. The middle two are basically the same version of this, right? 0, 1, 0, 1. When we have that, well, the OR gate says, yeah, look, he's on the list. You can come in. NOT dot's like, nah. The AND gate says, no, sorry, you both need to be on the list. NOT dot's like, yeah, now let him in. Just to be like spiteful or something. Anyway, but the thing is, this AND gate says, no, I'm sorry, you both need to be on the list, and so it doesn't get through. Right? Here, if the case of we have all of the ones, well, the OR gate would have let them in, the AND gate would have let them in, but the NOT dot in both cases flips and says, nah, not allowed in. So if they're not allowed in here, the AND gate says not allowed in here. So the answer is 1, 0, 0, 0, yeah, all the zeros. Okay, no explanation there in the answers, it just moves on. Okay, digital TV uses Zener diodes. Now, we have talked about Zener diodes once, I'm sure, but let's have a look. Okay, so if we go to Zener diodes, this is what a Zener diode looks like, and it basically doesn't work until the voltage gets high enough, is the thing. So if we go, it is on page in the Copeland book 212. Zener diodes are diodes that are one-way component at a certain voltage. Beyond that voltage, the current begins to flow in both directions. Okay, sorry, a student just corrected me and says they're one way up to a certain voltage, just in case I said the wrong thing. Originally I was going to say air, but, you know, I suppose I should try and do the best I can. Okay, we've got a drawing question. I just had a couple of questions about the diode thing, so I'll just quickly reiterate. I don't know how... I could look up how they're pronounced. I don't even care. Okay, so these diodes, I'm going to call them Zener diodes. I don't know what they are. So the idea is when the voltage is low, they don't get in. When the voltage is high, they go in both directions. Yeah, so low voltage, one direction, high voltage, two directions. Now, what's the effect if you run an AC current through there and you run through a diode? Just as a question I have, if we just run a AC current with a diode, what we'll get is a half-wave rectification. Yeah, so we'll just have the bump, bump, bump. Yeah. That's where we have multiple. We have the four rectifiers. Yeah. Okay. So the next one, we have a question. It's a drawing question, assembly drawing, right? I'm just going to show you the answer in the book, which looks like that. Now, they've asked for a half-section view. So, things to remember. Obviously, they've drawn this with CAD, which is just totally cheating, right? But here's what we're going to look at. A couple of things to point out. First of all, note the difference between the thick and the thin lines. Center lines are thin, section lines are thin. If you're ever drawing hidden detail, they're thick, but otherwise, thin lines, thick lines. Okay, these section lines are drawn neatly at 45 degrees. Yeah? So they should be evenly spaced at 45 degrees. Now, it doesn't have to be perfectly accurate, but I would say I've shown you a trick on how you can do that with your set squares. Do that. Okay, the thread. So it's important you draw the thread correctly. So the thread going up to the right depth is important, right? That little notch there to show where the thread starts. The thread, so the 45 degrees here where the thread finishes, right? The other thing, so this is not a terribly hard question. The last part that I would say that you need to pay attention to is whether or not we show across the flats or across the corners. In this case, so if it's across the flats, you just see one line, right? One line here. Because across the corners we see two. You're seeing one half of the, we're seeing three sides of the hexagon, whereas alternatively we can see one half of the hexagon. So that's important when we look at the drawing, that the hexagon, see how we can see a flat side of the hexagon. We're not looking, if we were looking in that direction, we would just see one line. Yeah, one line, exactly in half. But it would be a different width, which would be 1.6 times the diameter, not 1.8 times the diameter. And yes, because it's a nut, how deep is it? That's a good question. They've said it's an M10 bolt, and they expect you to know how deep that is. There's no dimension there, right? Because they're just jerks, right? But so the rule is, if it's the head of a nut, if it's the head of a bolt, it's 7 times the diameter, 0.7 times the diameter. If it's a nut, it's 0.8. Yeah. So this should be 8. If we were to measure this, I'm going to go on record as saying it should be 8 millimeters. Except I think this might be at scale, 2 to 1. Yeah, great. Now that's 6 marks. That's a good question for 6 marks. Probably 1 mark is because people forget to do it at scale, right? But that is probably where 6 marks. Yeah, no omissions, no errors. Yeah, that you remember to do it as half section. The correct anyway. Yeah, you could freehand and still get some marks. Yeah. Now they do give some marks for general shape. So if you're wobbly and you don't get on the line, you're gonna lose marks. But you'll definitely get most of the marks, because what they care about is they care about line quality, they care about sectioning, they care about getting, sectioning means 2 things, like the thread here, that there. They'd care about the bolt, they'd care about scale. So if you just freehanded it, you'd probably still get 4 of those marks right.
So what's that section bit there above the bolt?
Above the bolt, this is the thickness of, when they've folded this piece that's holding the thing together, there's a piece of steel where they've folded it. Let's have a look. Can you see how there's a piece of steel where they've folded it? That's what we're looking at. We only do half because they said draw a half section front view.
Okay.
How many? Because from what you can see on the assembly drawing, it looks like an oval. But then it actually looks like it's a full circle on this drawing. Because
Circle.
How do we know that's just because the thread stops there?
So this bar, the threaded bar, is that?
Yeah.
Oh, I see what the question you're asking. Okay, so when we're drawing the section half section view, yeah. Okay, I see what you're saying. I see the question now. Okay, you ready? I think that if you're cutting through, we're not cutting through that shape, are we? So where's our section? Our section is going through the middle, right? Through the middle of this thing. And when we cut through the middle, we're not going through that material. So that should not be a thick dark line. That should be a thin dark line. That's sort of an advanced technique. So yeah, that should be a thin dark line. That's my position. That should be it. Did I just say thin dark line? Yeah, thin dark line. Yeah, so it should be thin. And this line here should be thick. Yeah, is that what you're suggesting it should be? That's the correct answer?
I'm not sure.
Look, the point is, I think that it's contentious enough that the HSC example gives it. I could draw my own one and say this is what I think is a more correct answer, and I could debate it. But for the moment, I don't think you would have lost a mark if you had drawn it slightly differently. If those lines there, as long as they can see, and my understanding is as long as they can see some correct use of thin and thick dark lines, that's all they care about.
Okay.
Yeah, as long as they can see a differentiation in your line type, that's enough. Now, when I was at school, that was all about, look, you need to be using a 0.5 mm pacer and a sharpened HB pencil and a 2H pacer. Look, the reality is I think that the standard of drawing has dropped so low now that as long as they can see a differentiation between your line types, they're happy. Okay. Polypropylene is lightweight with a low coefficient of friction, making it ideal for use in sleds, which require these properties. Oh, sorry, this is not a question, this is the answer. Okay, we've got a sled. Explain how the properties of polypropylene, which is the number 5 plastic, make it suitable for this application. Okay, so explain, we're talking about cause and effect. So, polypropylene is very good at being injection molded, which means that we can produce a high quality product very quickly and cheaply. Yeah, or efficiently is a better word than using cheaply. For some reason, they don't like you talking about money in educational settings. So, polypropylene can be injection molded, which means it can be manufactured very efficiently. It can be colored, which means that it's more aesthetically appealing, and then, again, I would say commercially... Sorry? Yeah, you can if it's injection moldable. That's a property. I would still say that it can be. Let's have a look. Let's see. Polypropylene, so they talk about the coefficient of friction. One of the students just said that it means it slides. It's easy to mold, boom, 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 and provides high flexible strength and durability. Think lunchboxes. Are lunchboxes, are they durable? Yeah, they flexible. Yeah, lunchboxes made out of polypropylene. Yeah, there's plastic chairs. Are they flexible? Are they durable? Yeah. Yeah, oh look, but they're pretty good, right? Okay, next one. Now, they're asking you to describe the injection mold process. Okay, for 3 marks. Now, we have a number of times I've put this on Facebook for you guys, right? The 3 key things you need to talk about. Granulated feed is fed via a hopper, right? It's usually colored. You don't need to say that, but it is. It is then passed through a screw, which uses heat and pressure to produce melt. When sufficient melt, so molten plastic, is built up at the front of the nozzle, it's injected into a mold and then allowed to cool. The mold is removed and the object is released. Now, you can add to that a little bit by talking about flash being removed, right? Flash being the stuff you scrape off the side, because the rise is the runners where it's joined. But you don't need to talk about that, right? For 3 marks, granulated feed is added to the hopper. It is through the screw. It's heat and pressure produces melt. When sufficient melt, it builds up at the nozzle. It's injected into a mold. The mold, it's allowed to cool and then released from the mold. That's it. That's all you need. Yep. The screw is important. Yep. I'm willing to bet that the word screw is. This could include rotation molding. Okay. They're heated by friction internally and heated until wrapped around the outside of the machine, forced into pressure, still mold a desired shape. Once solidified. Yeah, it doesn't talk about the screw here. I'm disappointed that it doesn't say that. And it talks about being ejected, and then the flash is trimmed off and then polished. Okay, so this is a question I've had for a long time now. So this is a picture of thermoplastic, thermoset. There's slight differences. You don't need to talk about the being tapered, right? For thermoplastic, it's tapered. Thermoset, they don't need to because it's a exothermic reaction. It produces heat as they react. It also only uses one hopper. Here we have the colorant added. So I have the short answer. Feedstock added into hopper, fed into barrel till sufficient melts. Fill shot is injected into the mold and allowed to cool. Here's a slightly better answer. And then going back. Up. Here is a video that you can use. Yep. So there's the link if you want to painstakingly type that into the internet because you're not in the Facebook group. Okay. Just before we go, we'll see.